Yeah.
I request
Okay,
you to say a
thank
few
you.
words about yourself and your contribution.
Yeah, so actually I am associated in Department of Mathematics and Humanities at SVNIT Surat. We are working on that active hypergeometric functions from 2013 onwards. Okay, I have done my PhD at SVNIT Surat itself under Dr. A.K. Sukla, who is now Professor of Mathematics here. And I'm lucky to meet Professor Srinivas Rao on different occasions in IMS, Indian Mathematical Society Conference, as well as in ICNG, Mysore, University of Mysore. In just prior to lockdown in 2019, we have met there.
Yes,
and it is my proud privilege to be associated with you. And
thank you.
With your chair, I am presenting my talk. Thank you very much. And on another part also, I am fortunate to give the talk in an international webinar of special function and their applications hosted by University of Kerala, Department of Mathematics. Thank you, the organizer, for giving me the invitation to deliver the talk. Okay, looking into the contribution by Professor Rao and others, I am a very small person doing something in special function, and from my talk you will get the glimpses what I am doing here at SVNIT. So I'll go for my talk. Okay, sir. I'll continue now.
Yes, sir. Please.
Yeah.
And
So,
I have only one
outline
question
of
to
my
the
talk.
chairman, to the organizers. How much time, sir? 1 hour from now, or?
Yeah, it is 1 hour from now.
Thank you. So 1 hour from now.
11:30. Yeah, we have 11 up to 11:30.
Yeah. Okay. Okay, I'll try to finish before the talk, and we'll go for the interaction session also. Okay. Okay, so my talk, it will be consist of introduction about the subject, especially the subject of special function and hypergeometric function. Then I'll go to Wright type hypergeometric function. Then we worked on actually in extended Wright type hypergeometric function, and where we are working that also I'll highlight. And several properties of extended Wright type hypergeometric functions also we'll discuss. Then we'll go for some applications and we'll derive some theorem and proof also. I'll give here the brief proof, not the extended proof we will provide here in the talk. And if you go to the study of higher transcendental functions, which also sometimes we are calling it as a special functions, it is grows up with the calculus and is consequently one of the oldest subject, which is considered as a branch of analysis previously. Now they are associated with the differential equation. They are associated with in what in Lie algebra. So several higher. It is not like only one part of analysis or any other things. It has several connections. Even in quantum mechanics also, what Professor Rao has told like that. And perhaps the word hypergeometric appeared in Wallis' writings, and the hypergeometric was introduced by Leonardo Euler, who also found an integral representation of it. Okay, so we have derived the hypergeometric series from the hypergeometric differential equations. Not only we can derive the integral representation of the hypergeometric function as well. Although Euler obtained the hypergeometric functions, and this is the 2f1 functions. If you go for here, we are writing AB, then semicolon. So this is the representation. It is also sometimes represented as 2f1 functions, which is called the Gauss hypergeometric function. And so, although it was obtained by Euler, but we know it as a Gauss hypergeometric function. So this is the picture of Johann Carl Friedrich Gauss. Okay, so the maximum 2f1 functions we credited as we called it as a Gauss hypergeometric function. Then in the 19th century, using the results of Gauss, Kumar, Gorsat, Schwarz, and Klein, and many others, the hypergeometric series in function theory becomes apparent. Not only that, okay, Professor Srinivas Ramanujan also in the period 1900 and 1920, he has also extensively studied the hypergeometric series, even in most cases in the unpublished notebooks without complete proofs. And this is the motivations of our study also. As is true of all other works of Ramanujan, it remains intriguing to know how he arrived at those results without having a formal knowledge of the transformation theory of the general hypergeometric series. It is therefore always interesting to investigate the possible unorthodox methods used by him, which go to establish his invincible originality and intuitive genius. Now I am going towards from hypergeometric function. Now I am going towards right type hypergeometric function. Sometimes it is called also Wright function. So it is named after British mathematician E.M. Wright. The full name is Sir Edward Maitland Wright. Okay, and the work appeared for the first time in connection with investigations in the asymptotic theory of partitions. So even right functions has the applications in partition theory also. Those who are working in number theory and partition theory, they may have extensive knowledge about that. Later on, Wright further extended this function in the form of generalized hypergeometric function, which is known as Wright type hypergeometric function. Many researchers often interesting results, including contiguous relations, integral representations, and recurrence relations of generalized Wright functions and their properties. And what is our motivations? There is a connection between Gauss hypergeometric function and Wright type hypergeometric function, and we have investigated that connection and we derived several properties and investigate several properties of this extended Wright type hypergeometric function. Now I will define this function, then we'll derive several properties also and some applications also. This is the work I will present. And there are enormous scopes to study the basic properties, the fractional calculus approach. So I'll use some methodology of fractional calculus in our study also, and we will use some incomplete gamma functions also. So these are the things we'll use as a tool in my study. So this is the definitions of mathematically, if you represent Gauss hypergeometric functions, this is 2f1 function f a b c z, which is the infinite series representations, which is represented as function n equal to 0 to infinity a. This is the factorial function where it is defined by this way. Okay, n it is nothing but a plus 1 up to a plus n minus 1. Similarly, so it is 2f1, so 2 in the numerator and 1 in the denominator. That's why it is 2f1. And if you see the representation also, ab, then semicolon, then another parameter, c, then another semicolon also, and z is the argument of the function. So it is represented as summation n equal to 0 to infinity a n, b n, c n. So all this is a special function, international linear. All are familiar with this. So I will not much concentrate about these things, but whatever the work we have done, I must focus on that one. Okay, you maximum of you know this notation lambda b, where lambda b both belongs to c. This is denoted a Pochomer symbol, which is denoted by in the representation of gamma function. Okay, so this is the representation of gamma functions, which is 1 when p equal to 0. So again, if I put 0 here, I will get 1, and when it is not equal to 0 and it is denoted in the form of n, b belongs to n, then it will be nothing but a product of this lambda, lambda plus 1, lambda plus n minus 1. And this is also, we'll assume that like factorial 0 equal to 1. So we'll assume that 0, 0 equal to 1. And gamma functions also exist. So there is a little discussions in the reference to it is given. And the classical generalized hypergeometry. So when there it was 2f1, if we extended this in general form, pfq. So pfq is what? In the numerator we have p number of parameter, and the denominator we have q number of parameter, a1, a2 up to ap, and b1, b2 up to bq. So p number of parameter, if you see here, a1n dot dot dot, these are product, apn, and b1n, b2n, get to the power n by factorial n. So here this will be happen only if p equal to q plus 1 mod z less than 1. No denominator parameter is 0 or negative integer. So this is called the classical generalized hypergeometric function, or simply sometimes it is called the generalized hypergeometric function. There are extensive theory appeared in generalized hypergeometric functions. There are several books, and Gaspar Rahman, basic hypergeometric series, They are a very, very good book where the properties of generalized hypergeometric function can be found. Then we will come back to right type hypergeometric functions. So what it is here also, this is also the p psi q. So right functions we denoted as psi function, where in terms of gamma functions we represent here also. If you see here, we have alpha 1 dot dot up to alpha p. So p number of gamma functions, alpha 1 plus beta 1 n, alpha 2 plus gamma alpha 2 plus beta 2 n, up to gamma alpha p plus beta p n. And in the denominator, we have gamma rho 1 plus mu 1 n, gamma rho 2 plus mu 2 n, up to gamma rho q plus mu q n, and z to the power n by factorial n. And this is the convergence conditions that beta r and mu t are real positive numbers, such that this will be happen. Sorry, that this is 1 plus summation t equal to 1 to q. Q is the number of denominator parameters mu t, and summation of all the numerator parameters, it will be greater than 0. So this is the thing, it will be satisfied, then only this functions will exist. And not only that, when beta or mu t are equal to 1, then this one differs from the general hypergeometric function only by a constant multiplier. So it will be not special type right type hypergeometric functions, it will be some multiplication of generalized hypergeometric functions. Several researchers like Dostenko, Malvichko, and others has generalized. They have worked on generalized form of hypergeometric function, and the special case generalized form of the hypergeometric function considered as the form this. So this is also another type of hypergeometric function form. Here, these are the two new parameters which have been introduced, and this omega mu, it is denoted by this way. So it is also 2r1. So this is not like hypergeometric functions, but it is hypergeometric type function. So that's why it is 2r, and omega mu is extra here. So how it is defined? It is defined by this way: gamma c, gamma a, gamma b, then summation of this a plus n, gamma b plus omega by mu n. Similarly, in C also C plus omega by mu. Mind that here we have no omega by mu is there, but in case of B and C, omega by mu is there. So this is the new functions which is defined in 1. And in 2001, Vichenko et al., they have defined the right type hypergeometric function by taking omega by mu equal to tau. So there we are getting only one parameter. There two parameter was there. Here omega by mu has been taken as a tau, which is greater than 0, and we are getting another function. This is also, and which is, and the various properties of that functions has been studied by Snell v. Rao, which is denoted in reference 1 and 2. And in 2017-18, Parmar, R.K. Parmar, who is also one of the speaker of this international webinar, they have introduced the following extension of the tau hypergeometric functions, which is denoted by this form, 2r1 tau. So here also omega mu is not there, tau they have used AP. So this AP has the form that these are the generalized gamma functions. So generalized gamma functions also we have to define, and this notations we are using: summation n equal to 0 to infinity apn gamma b plus tau n, gamma c plus tau n, z to the power n by factorial n. Okay, and this is the convergence condition. And this is the generalized Pochhammer symbol we have used here. So this is the same way, and the definitions it is denoted gamma p. This is p parameter, p type gamma function, gamma p lambda plus p, gamma lambda, and it is denoted by this way in 8 form. So when it is a very particular case, when you put p equal to 0 and lambda b belongs to c, that time you will get the original classical Pochhammer symbol, but this is generalized Pochhammer. And what about the gamma pz? Whatever we have denoted here, this gamma pz is denoted by this way. This is called the generalized gamma function, which is introduced by Chaudhary and Juve. Okay, the external studies carried out in this monograph. Okay, so gamma pz it is denoted by 0 to infinity. In place of here, if you see here, it is not e to the power something, it is minus t minus p by t. So that's why it is called P generalized gamma function or simply generalized gamma function. And this is the convergence conditions. And if you put P equal to 0 and when real P greater than 0, that time you will get simple gamma function. And so we have used the previous results also in 2013 Srivastava. Okay. They have defined a family of the generalized and eccentric hypergeometric function in the form of this. So they have used this notation. Okay, the first parameter, it is of this form. So, and the representation in terms of series form, it is given by this way. So they have also used the generalized Pokémon symbol as well as generalized gamma functions, and which is generated by this way. If you see here, this is more complicated. It is called generalized and extended Pokémon symbol. So our study, why we are writing right type extended hypergeometric function, it is because we are using the generalized and extended Pokémon symbol. That's why we are using the same name, right type extended hypergeometric function. So this is the generalized and extended Pokémon symbol, which is defined in 1 again. And this is the notations, which is the, here it is gamma p KL L belongs to n0, lambda plus b, gamma p KL L belongs to n0, lambda b belongs to c, provided that the series on the right hand side of 10 converges. And the function gamma p KL L belongs to n0 z is the generalized and extended gamma function, which is, so here we are using also extended gamma function. So what is extended gamma function? Here if you see, we are using this notation, capital theta, and capital theta is this way, which is also due to Srivastava. Okay, so this is the, so we are using this type of function, extended gamma function, generalized Pokémon symbol in our notations. So that's why we are writing right type extended hypergeometric. Now we will introduce our function. So here, this is the capital theta function, which is generated by this way. Okay, and this is also the asymptotic convergence. So that also, this is the convergence conditions also, and for some suitable constant n0 and omega, depending essentially upon the sequence KL L belongs to n0. So this is the preliminary of the study, and we taking that into our account and going through the properties of the previous functions. We have introduced an extension of the tau right type hypergeometric function, and we have used the generalized and extended Pokémon symbol defined by 11, and we then derive several classes of generating relations involving this extended tau hypergeometric functions. Okay, and not only that, whatever the result it is given by Parmar and Srivastava, that we have got as a special case. So in terms of generalized and extended Pokémon symbol defined by 11, we have introduced this function. So in our next all the slide, I'll involve this function, which is defined by 14. Okay, so this is the functions defined by us, and we have extensively studied these functions, and we have derived different properties and applications. So in the remaining all the slides, I will use this 2R1 function in our study, and for some special cases, we'll reach to Padmar's as well as Srivastava's result. So in a very special case, when KL is 1 and P equal to 0 in the denominator, in definition 11, the generalized and extended Pokémon symbol will reach to the generalized Pokémon symbol, while 14 will set to the extended tau hypergeometric function defined in 7. And if in 11, so I'll get, if you put particular value, I'll reach back to the some classical functions. So now we will discuss about properties of the extended right type hypergeometric function. So the extended tau right type hypergeometric function, this is the integral representations we have derived. Okay, so 2R1 AP KL belongs to N0 BCZ. These functions can be represented in terms of integral as we will get the same form of the 2F1 functions type gamma C by gamma B, gamma C minus B, integration 0 to 1 TB minus 1 minus T. But here we will get this. Okay, so this is the integral representation of the which we have derived. Okay, so how we have derived that preliminary prelude of that proof at then given, we are using the classical beta function, so which is defined by this, and using that notations we can, and all the definitions of extended Pokémon symbol, generalized gamma functions, using that results we have got the integral representation of the functions defined by this. So then we have used the binomial coefficient, generalized binomial coefficient. Binomial coefficients, if we write lambda mu, which is very easily can be written as factorial lambda like that way. But we have used the generalized binomial coefficients. Here we are taking lambda mu belongs to C. Okay, so when you are taking lambda mu belongs to C, we represented this in terms of gamma function, which is denoted like in 17. What is that? That is gamma lambda plus 1. So if it is in n, that time you will get factorial lambda like that, factorial mu by factorial lambda minus. Okay, not only that, we know that NCR equal to NCN minus R. So same thing you can go for when lambda mu belongs to C as well. So that's why it is called the generalized binomial coefficients. And when you, in the special case, if you put mu equal to n belongs to n0, we have this notation like that. Lambda n, you will get minus 1 whole to the power n minus lambda n by factorial. And we will get the generating relations, which will be equal to for the extended tau right hypergeometric function. So this is the generating relations for that. Okay, so this is the generating relations of the. Mind that we are not writing generating function, we are writing generating relations. Okay, so we are not getting exactly the generating function form. We are getting this way. And here also we have the functions. Here also we have the functions. So that's why it is generally type of generating relation. So that's why we are using generating relation. So this is the generating relations of the function 2r1 tau, which is defined by us. Not only that, other way also, here it is t to the power. Here, if you see here, we have changed here z into 1 minus t to the power tau. Here z by 1 minus t. So if you change the parameter, you will get the another analysis. So proof is also given. I will not go for the details of the proof. Okay, if anybody has any doubt after this presentation, you can ask me. Okay, so it is the things we are using the definitions. We are using the definition of gamma functions. By using that, we are going for the proof. Okay, we are taking the some inverted order of the summations. Okay, and now by applying the generalized binomial expansions, we are using the binomial expansions also. This is very famous. 1 minus t whole to the minus a can be written as this way summation n equal to 0 to infinity n to the power n by factorial n. So we are using that things to prove the relations. And not only that, in order to derive assertion 20, we use this as well. Lambda n gamma 1 minus lambda minus n divided by gamma 1 minus lambda minus n plus tau k, which is can be represented as equal to lambda minus tau k n gamma 1 minus lambda divided by gamma 1 minus lambda plus tau k. And we apply the similar steps. By the way, we have proved 19. So 19 and 20 has a similar proof. Only the difference is this one. So that we have used, and we will get the second representations, second generating relations. And we are using the result of Parmar as well. Now we next introduce the sequences psi n, lambda tau z n belongs to n0 and theta n. So we are using two sequences psi n and theta n of the extended tau hypergeometric functions. How we have represented? We have represented in terms of 2r1 tau function. So this is the notations we are using. Psi n lambda tau z, which is nothing but the 2r1 tau APKL belongs to n0 lambda plus n. So it has also, if you see here, two parameter, it has one, so 2r1. Okay, z. And theta has a different notation. So here we are using b, but here we are using 1 minus lambda minus n instead of c. So that's why we are denoting that theta. Okay, this is psi, this is theta. So which is represented by 21 and 22. We can get several properties of this. Okay. So So how we can prove it? We can prove by this, by substituting for the sequence in psi n and using the definition of the general binomial coefficient. So we have introduced binomial coefficient, generalized binomial coefficients in 18. So using that definition and as well as the extended tau right hypergeometric functions, which is defined in 14, and inverting the order of the summations, the left hand side of the resistance 23 has been established as this, and so this will get both sides. So you can write psi this as this way. Okay, so this is the lessons we will get, and we will apply the general binomial extensions, which we will get at the 23. Similarly, we can get the 24 as well using the same way by what we have used for 23. Then in the next part, what we will go for, I will go for how this function is related with another type of special function. So 2R1 tau, it is related to with McDonald functions also k alpha j. So this is the relation, the 25. It is giving us the relations between k alpha z with 2R1 tau. So 2R1 AP B C Z can be represented as this way: 2p alpha by 2 gamma c gamma b gamma a. Mind that here gamma c in the top, gamma b gamma a, and that can be represented as a summation of n equal to infinity McDonald function of here it is in place of alpha. Here we are getting a plus n, and argument is 2 root, and this is the summation of n. Okay, this is the McDonald. Okay, so what is McDonald function? This is nothing but a modified special function, third kind. There is modified special function of first kind, second kind, and third kind is has a name which is called the McDonald functions. And what is that? It is represented in terms of this. This is the definition of McDonald functions, which is given in 26. K alpha z, which is nothing but z by 2 whole to the power alpha by 2 0 to infinity e to the power minus t minus z square by 40 to the power minus alpha minus 1. It is different from the gamma functions as well. So this is the representation of McDonald function. So we are showing in 25 what do we want to show? We want to show that how these two R1 functions it is related with McDonald function. Then RK Parmar also they have given the representation of the generalized Pockmark symbol, which is given in 27. So that we will use also, and we will derive the this 2R1, how it is related to R1. So that also we have shown in this result. 2R1 tau APBCZ can be represented in terms of this. And in terms of representation of McDonald functions, we will get this. So this is the result we have used for the from the Parmar, and using the definition of McDonald functions, we will derive this result. Then this is the differential formula. So if we take dz of z to the power 2 R1 function, then we will get z to the power a minus 1 a 2 R1 tau. Here this is the case. So what we are getting AP here, but here we are getting a plus z. And not only that, there is another function also. So this is the differential formula we will get for the 2 R1 tau functions, which is given in 29. And so how we have proved? We have used this property a plus n APN. So this is the definition of the generalized Pockmark symbol. So using that, and not only that, we are differentiating and using this property of Pockmark symbol as well. So using that, we have deduced our result, which is cited in 29. So this is the way of proof we have done, and this is complete the proof. We have done some derivation, so it is not very complex to prove it, but you know that these are the little bit one parameter. If it is problem, your solutions will be discarded. Okay, so when you are doing special functions, big calculations, you have to be very much focused on the parameter. Okay, and the gamma functions has a very important role also, so that also you have to look into. Then integral transform. So here we have find several integral transform of the functions introduced. So we have find the beta transform like the Euler transform of 2 R1 tau functions. So here, if you see here, we are using the beta transform. So 0 to 1, z to the alpha minus 1, 1 minus z beta minus. So we are using this functions transform. Okay, and what we will get? we'll get beta function, and here this has been extended. So here 2R1 is there. Here we are getting 3R2. So this is the extension of the 2R1. So you will get 3 parameter in the numerator, and the denominator we have 2 parameters. That's why it is called 3R2 functions. So here we are getting this. Okay. And here this is a definite integral with respect to z. So z will be dissolved. We will get function of x, because here it is, if you see here, xz tau it is there. Xz tau it is there. So z will be dissolved. We will get x. So how we have done the proof of that? We have used the series representation of the function 2R1 tau, and we have changed the order of the integral as well as the summations. So you know that changing the order of the integrations in double integral, triple integral will play an important role to derive several results. So we have used that trick into our proof. So and some derivations will lead to this 3R2 tau function. So this is called the beta transform of 2R1 tau function. Similarly, we have done Laplace transform as well. Okay, so this is the result using these conditions. So it is not directly we are getting the result. If we will assume ABC alpha belongs to C, tau sigma belongs to R plus, real part of B greater than 0, real part of C greater than 0, real part of alpha greater than 0, not only that, real part of S greater than 0 and P greater than 0, and x by s to the power sigma less than 1. So we are using x by x to the power sigma. So if it is considered z, so mod z less than 1. So like that. So if these all the conditions it is satisfied, then only we the Laplace transform of these functions it will be exist, and this can be represented. If you remember here beta transform, we are getting 3R2 here when we are doing the Laplace transform 2R1, but here we are getting 3R. Okay, so this is also another transform we are finding. So our basic research is nothing but the special function and integral transform we are doing. So here we are finding the integral transform of the function, taking this type of function as a kernel. Okay, so this is the here Laplace transform we are using. We are using the exponential function as a kernel, and here also we are finding the Laplace transform of this function to be z to the alpha minus 1 into this. The proof is also again we are using the series representation of 2R1 tau. Then again we are changing the order of the summation as well as the series, and we are getting 3R1 tau functions. Okay, so this is the proof of that. Okay, is it okay? Am I audible and everything is fine? Audience end?
Very good.
Hello. Okay. Next. Then we are going for finding the Whittaker transform also. So if you see here, this is the things W, lambda mu, sigma t, and we are using the 2R1 tau. These functions we have taken extra to get the result in proper set. So this is not in the Whittaker transform, but we are using this such that I'll get this result in terms of some hypergeometric representation form. So this function also here extra. This is actually not x. This is just multiplications. I cannot write this result into the continuous form. This line, this space, it will be sorted. So we have written into this to 4R2 tau. So this is the result we have got for the Whittaker transform. The again for this proof also simple. So what we have done for Whittaker transform, we are using Whittaker function. So W lambda mu t. This is the definition of Whittaker function. Zeta function. We are using zeta, not zeta function. This is zeta to the power. We are using that. And not only that, real part of lambda plus mu minus half, it will be less than equal to 0. So this is the conditions for the Whittaker functions to be exist. Okay, and this Whittaker function has been considered as the kernel of the Whittaker transform. Again, here also we have done the same trick. We have substitute sigma t equal to v, and we have changed the order of the integration as well as summation, and we have derived our result. But the result we got the result in terms of 4R. Okay, and not only that, we have used this result also. How Whittaker functions. It will be integral representation of Whittaker functions we will get in terms of gamma function as like this. Then we have done some applications of these functions by understanding this. So using the theorem stated above, we derive various interesting classes of linear, bilinear, bilateral, or mixed multilateral generating relations for the sequences. So if you remember, we have denoted some sequences psi n and theta n. So this in 20 and 22, which is represented in terms of two R1 tau functions, which is defined by us. So these sequences play an important role. So we are doing this. So we are using some non-vanishing functions. Okay. Capital pi mu, zeta 1, zeta 2 up to zeta s of s complex variable and involving a complex parameter mu. So this mu is complex parameter as well as zeta 1, zeta s. This that belongs to capital N. Then this omega mpq z, it can be written in terms of pi form. And these two functions we are defining in terms of pi as well as two sequences psi and theta. This is for psi, this is for theta. So this is the representation of this function. Okay. Then there is another representation also, capital theta, lambda p mu sigma, which can be represented in terms of pi also. Not only we have used pi also, small pi, lambda p mu. This also represented in terms of capital pi. Here it is psi, here it is theta. So what is the case? The sequences psi and theta are defined, which is in 21 and 22. So this is, if we define capital theta, capital pi as this way, then they can be represented in terms of omega 1, omega 2 by 35 and 36. So we have not given here the proof of this, but this is a rigorous things. So we have given some short proof. Okay. So these are the things. We are using the notations and whatever the assumptions we have taken, that we are using here to prove this. So we have thus completed the proof of the assertion and the assumption that the double series involved in the. So there is the concept of double series. So that also how the double series concept we are using to prove that result. The same method of proof of the first assertion 35 can be applied in order to derive the second assertion 36, which would yield the bilateral or mixed lateral generating relations for the sequence defined by 22 in terms of extended tau Wright type hypergeometric functions. So R1 defined by 14. And if we define the sequences psi n lambda tau z n belongs to n0 and theta n in terms of Parmas tau hypergeometric function, then we will get the special case 2R1. So this is the representation. This is the particular case. Okay. And similarly, capital theta n, which is represented in terms of our function like this. Then the generalization 23 and 24, 35 and 30 still hold true for the sequences defined in 38 and 39. Again, we can further generalize the tau Wright type hypergeometric function 14 in terms of this way also, PRQ tau like this. So this is provided that the series on the right hand side converges, and by applying the same methodology described in the aforesaid mentioned theorems, one can derive the analogous generating relation involving the function 40. I am very much grateful to SCRB for doing this study at SVNIT. These are the references of my work. I have used the two R1 functions, which is given by this integral, which is appeared in integral terms of functions. Then we have used the Parma result also, then Srivastava result also, which is appeared in applied mathematics and information science. These are the work we have published in connection with this result. Thank you very much. If anybody has any questions, please let me know.